In the section of the course on matrices, we defined eigenvalues and eigenvectors for matrices, and we're now going to do the same for linear maps. Here's the definition. If we take a linear map T from a vector space V to itself, and if A is a scalar, so an element of the field over which V is a vector space, then an A eigenvector for T, otherwise called an eigenvector with eigenvalue A, is a non-zero vector in V with the property that T of V is just A times V again. Next, A is an eigenvalue of T if there exists an A eigenvector for T, or an eigenvector with eigenvalue A for T. Finally, an eigenvector for T just refers to an element of V which is an eigenvector, an A eigenvector for some value of A. So it's important to note what's happening in this definition. Eigenvalues can be zero, but eigenvectors are never the zero vector by definition. So let's look at some examples. In fact, we're going to revisit an example we've already seen, which is if the linear map T from R squared to R squared, defined by T of xy, is minus 16x plus 6y in the first coordinate and minus 45x plus 17y in the second coordinate. We've actually seen already examples of eigenvectors for T when we worked with this example in our video on matrices of linear maps, because we showed that T of 2, 5 is equal to minus 1 times T 2, 5 times 2, 5, which tells you precisely that the vector 2, 5 is a minus 1 eigenvector for T. And you can also check that T of 1, 3 is 2 times 1, 3, so it's 2, 6. So that means the vector 1, 3 is a 2 eigenvector for T. And it's easy also to see that any non-zero multiple of the vector 2, 5 would again be a minus 1 eigenvector, and any non-zero multiple of 1, 3 would again be a 2 eigenvector for T. For example, so let's say if we multiply this by minus 1, minus 2, minus 5, that would be again a eigenvector for T with eigenvalue minus 1. As another example, let's consider our differentiation map from the vector space of all polynomials in one variable x over the real numbers to the vector space of all polynomials in one variable x over the real numbers. So that's called d, and d of f is defined to be the derivative df by dx. Then if you look at the constant polynomial 1, the derivative of the constant polynomial 1 is 0. And that means the constant polynomial 1 is an eigenvector with eigenvalue 0, because d of 1 is equal to 0 times 1. So again, to emphasize, eigenvalues can be 0. That's absolutely fine. But a eigenvector must be a non-zero vector. So here, the constant polynomial 1 is an eigenvector for d with eigenvalue 0. We have to be slightly careful about fields and about which field the vector space we're working with is a vector space over when we talk about eigenvalues of linear maps. So I'll explain why that's the case in an example on this slide. So we're going to take A to be this 2 by 2 matrix. The characteristic polynomial of this matrix, chi A of x, is x squared plus 2x plus 2. So the eigenvalues of the matrix are the roots of that characteristic polynomial, and if you plug the numbers into the quadratic formula, you'll find that the eigenvalues of that matrix are 1 plus I and 1 minus I. And we can now define two different linear maps using the same matrix A. First of all, we'll define TA to be the linear map from R squared to R squared given by left multiplication by A. So TA of a vector x is just A times x again. Secondly, we'll define a map SA from C squared to C squared, which again is left multiplication by A. So SA of a vector x in C squared is just A times x. Now those are different linear transformations because they have different domains and different codomains. TA doesn't have any eigenvalues or eigenvectors, because an eigenvalue of TA will be a non-zero vector in R squared, such that TA of V was a scalar multiple of V again. In other words, it will be an eigenvector of A. But there are no such eigenvectors in R squared, because the only eigenvectors of the matrix A are complex vectors. On the other hand, SA does have eigenvectors, and you can find them in the usual way. You find the eigenvectors of A, and they will be eigenvectors of SA. So it's important to think about the field when you're thinking about eigenvectors. If you have a linear map from a real vector space to itself, then its eigenvectors must be real numbers. This just follows directly from the definition. It wouldn't make sense to multiply a element of a real vector space by a complex number, so there cannot possibly be an element of a real vector space which has a complex eigenvalue for some linear map. A nice property that eigenvectors have is that if you have two different, or in fact any number of different eigenvectors with distinct eigenvalues, then those vectors are linearly independent. You can see the full proof for any value of n of this inside the online notes for 0007. What I'll do here is just give a sketch of how to prove this when n equals 2. So when you have two eigenvectors with different eigenvectors. So let's say we have T of U is A times U, and T of V is B times V, and A and B are different scalars, and U and V are non-zero. They're not the zero vector in V, so that U is an A eigenvector and V is a B eigenvector, and A and B are distinct. I claim then that U and V are linearly independent. So let's suppose that we have two scalars x and y such that x times u plus y times v is equal to the zero vector. We're going to prove that x and y must both be 0, and therefore u and v are linearly independent. So let's give this equation, which I've just written down, a name. That's going to be equation number 1. We're now going to apply the linear map T to both sides of equation 1. Now, because T is a linear map, T of xu plus yv is the same as x times T of u plus y times T of v. And again, because T is a linear map, T of the zero vector is the zero vector again. But U was an A eigenvector and V was a B eigenvector. So what we really have here is that X times A times U plus Y times B times V is the zero vector. Okay, now you can see what we're going to do, because we now have two linear relations on the same vectors u and v. So we can just manipulate these to get the answer we want. So to spell this out, let's call this equation 2. And let's multiply equation 1 by a scalar. Let's multiply equation 1 by a. So a times equation 1 becomes a xu plus a yv is equal to the zero vector. Okay, observe the connection, right? We have the same term appearing in a times equation 1 as we had appearing in equation 2. So specifically, this thing and this thing are the same. So if we subtract the two equations we've just produced, something interesting will happen. So we will subtract a times equation 1 from equation 2. And when we do that, we'll get y times b minus a times v is equal to 0v. Okay, what have you got there? You've got a scalar multiple of a non-zero vector v. V is non-zero because it's supposed to be an eigenvector. You've got a scalar multiple of a non-zero vector which is equal to the zero vector. So because v is not the zero vector, so it must be that y times b minus a is the scalar 0. Alright, but b minus a is not 0. Remember, we're assuming that a is not equal to b because we're talking about eigenvectors with distinct eigenvalues. So because b minus a is not 0, I've got y equal to 0. Okay, similarly, we can get that x is equal to 0. And so we've shown that if we have any linear relation between u and v, so any equation of the form 1, then actually in that equation x and y must both be 0, and that proves linear independence of u and v. And we're done.